Okay.
All right, so I would say we can start. So welcome everybody to this month's edition of Ithaca. Our first speaker is Sebastian Wolf from the University of Regensburg, who's going to talk about higher category theory internally to an infinity topos. You have like about 30 minutes for a talk and then question time. Please, Sebastian, take it away.
All right. Yeah. Thank you very much for the introduction. Thank you very much for inviting me to give this talk here. It's going to be great fun, this whole meeting. So yeah, today I want to talk about what the title says, higher categories internal to an infinity topos. And this is all based on it will be some overview over a long ongoing joint project with Louis Martini. And somehow I want to start with something very basic that probably all of you know. So, well, I guess we all know what the definition of a category is, and somehow it's a very old observation, which I think was probably first due to Grothendieck or something, that you can interpret the definition of a category somehow internal to any other category with finite limits. So more precisely, if B is some category with finite limits, then you can define a category C internal to be a diagram that looks like this. So you have two objects in B, Z0 and C1. You're supposed to think of C0 as the objects and C1 as the morphisms. And then you have a bunch of maps relating them. So you have maps S and T, which you're supposed to think of taking the source and the target of a morphism, and a map going backwards, which you're supposed to think of, or somehow represents that you can take an object and then take the identity morphism on that object. And then you need one more datum, namely some map called comp, because this is supposed to be composition, which takes somehow two arrows such that the target of the first arrow is the source of the second arrow, and then it spits out a new arrow. So this is supposed to be the composition. Okay, and I mean phrasing this in this diagrammatic way, you need to, of course, add some more axioms. So you want to have associativity, some more composing with the identity, supposed to do nothing, and so on. Okay, so this is somehow how it goes in one category theory. Somehow I want to talk about, as the title already says, about this in higher category theory. Maybe I should say that for me, this higher is maybe not ideal. I should really say infinity one category theory. So this is really what I mean here. So for this, I somehow want to recall one perspective on infinity categories, namely via complete Siegel spaces. So let me give you a definition. So a complete Siegel space. So here I'm, by the way, already assuming that somehow there is a working theory of infinity categories. And then I can make the following definition that there's a complete Siegel space. This is simply a functor of infinity categories from C. So this functor is called C bullet, and it goes from delta op to the infinity category of anima. So this is, I don't know, I just started adopting this terminology. This is also sometimes called the infinite category of spaces or homotopy types or infinity groupoids, or whatever. There's a bunch of names. It's the free co-completion of the point. And you want this simplicial object to satisfy a bunch of conditions. First of all, you want that Cn, from there you have a canonical map into this fiber product here. So here I write this notation here. So C of 0 less than 1. I mean, that's just C1 again, but somehow I'm writing this somehow to indicate what the maps are. So this is somehow, you send 0 to 0, 1 to 1, and then you go on. And then that this is an equivalence. You require that this is an equivalence. And what this is basically saying is that you want the space Cn to be the space of n composable sequences of morphisms. Okay, so somehow it's similar to the definition that we had before, but now somehow we have this for all n. And you want a second condition, the so-called completeness condition, which says that the following here is a pullback. So maybe I should say what the map here is. So I think so here maybe I should have written in my terminology from above. So this would be 0 less than 2, and this would be 1 less than 3. And then it's hopefully clear what the map from here to here is. And somehow this is supposed to enforce that somehow, so this pullback, let's say this models the space of arrows that have a left and a right inverse, and you want to enforce that this is equivalently just C0. So somehow you want C0 to be the space of equivalences. This is how you can roughly think of what this condition 2 is supposed to say. Okay, and maybe I should have said, I mean, this definition, not exactly in this version, but still it's due to RESC. I forgot to say that. Okay, and then these simplicial objects, well, they fit into some infinity category, which I will denote CSS. So this is just a full subcategory of functors from delta op to anima, which satisfies these conditions 1 and 2 here. Okay. So far so good. So why did I tell you about this? Well, this is because of the following theorem, because this category of complete cycle spaces is in fact equivalent to the infinity category of infinity categories. So this is the following theorem, which somehow in its original form is due to Joyal and Tierney, but somehow they proved this in terms of an equivalence of model categories, and somehow in the language that I'm actually stating this, I think this was actually somehow a proof of this actually appeared quite recently by Fabian Hebestreit and Jan Steinebrunner. And the theorem says that the functor, I mean, I can give it a name, let's call it the nerve, from the infinity category of infinity categories to complete Siegel spaces, which takes infinity category C and sends it to the simplicial object, which is somehow given by, yeah, you can think of it as the restricted Yoneda embedding, so maps in the infinity category of infinity categories from, let me write it maybe like this, delta bullet. So you plug in the n here at this bullet, and you get maps from here to C. Okay, and yeah, the theorem is that this is an equivalence. Okay, so this is really another way of thinking about the infinity category of infinity categories. And now somehow, since, I mean, you can probably guess where this is going. I mean, these two conditions, they only involve finite limits. So, well, you can more or less copy the definition that we had above, right? So we call, if we have an infinity category B with finite limits, then an infinity category internal to B is now, I guess, what you expect. Namely, it is a functor from delta op now to B. So now instead of going to anima, we go to B. That's satisfying these conditions 1 and 2. I'm not spelling them out again, but somehow you have the exact same diagrams. They just live now in a different category, namely B, and you just ask that some maps are equivalences involving finite limits. Yeah. Okay, and somehow also as above, we again get an infinity category of such things, which I will denote cut B. So this is now a full subcategory of simplicial objects in B. Okay, and I mean, just for terminology reasons, I will not always say infinity category internal to B because that's a bit long, but I will just say B category instead. Okay. I mean, I think so. For example, one person that had already studied these before me and Louis was Nima Razek, who also proved some basic things about these infinity categories internal to some category finite limits, somehow in quite some generality. But somehow me and Louis have a slightly different goal, namely we do not really want to do this somehow for any B, but somehow we really want to focus on the case where B is an infinity-topos. And I mean, you later see a reason for this, but somehow morally speaking, an infinity-topos is such a nice infinity category that it has almost all the properties that the infinity category of spaces has, at least formally speaking. And therefore, almost all of higher category theory is also supposed to go through in this generality. But we will later also see something concrete where we actually need that B is an infinity-topos. Okay, so maybe some remarks. So first of all, there's somehow also a type theoretic approach to this kind of thing, which is in principle, which you can use to do the same thing. Namely, there's the simplicial homotopy type theory due to Riel and Schulman, and then it has been developed further, and some things have been proven in the simplicial homotopy type theory by Ulrich Buchholz and Jonathan Weinberger. And this is somehow, yeah, so they introduced some simplicial homotopy type theory, and then you can show that this can be interpreted somehow in simplicial objects in any infinity topos, and then somehow from this you could also get results about this. And then somehow, I guess, similar in spirit, there's also currently being developed a completely synthetic approach to higher category theory by Cieszynski, Knossen, Nguyen, and Walde. And somehow this would also subsume whatever me and Luis are doing, because somehow, again, yeah, the synthetic language is also so a model of this synthetic language is supposed to be exactly these categories internal to an infinity topos. Okay, are there any questions so far? All right, then let me give you the following proposition. I mean, this is somehow not something not something very hard. It's actually more an easy observation, but will turn out to be quite useful. Is that you can alternatively think of, at least in the setting where B is an infinity topos, you get that this category of B categories, cat B, is actually equivalent to sheaves of infinity categories on B. So my definition of sheaves of infinity categories on B is just a limit preserving functor from B up to cat infinity. But I don't know, if you want, you can also think of this as the Lurie tensor product, B tensor cat infinity. Some of this is basically the definition. So yeah, let me, I don't know, so that I at least give some proof, quickly prove this. This is not hard. So what was our definition of cat B? Well, this was by definition functors from delta op to B that satisfy these conditions 1 and 2. So maybe let me just write it like this. Okay, then we can apply the unit lemma to identify B with limit preserving functors from B up to spaces. So there's an equivalence between B and limit preserving functors from B up to spaces, somehow given by sending an object B to the representable functor. Well, and now we are in a situation that you probably are familiar with. Somehow we have here a functors into a functor category, and then we can of course swap these two arguments. But because limits in functor infinity categories are computed pointwise, we can also somehow swap these limit conditions. Because both this, I mean, this is literally just saying that it preserves all limits, and these condition 1 and 2, they also just involve limits. So you can also swap these to get somehow that this is equivalent to functors, to limit preserving functors now from B up into functors that satisfy 1 and 2 from delta op to spaces. Oh, now I started writing spaces instead of anima again. Sorry, I'm not consistent with this myself. So spaces is anima. Sorry. I tried to switch to this terminology, but I'm not fully used to it yet. Okay, but somehow, anyways, by this theorem that I stated above, the latter thing here, so now functor satisfying 1 and 2, that's exactly complete Siegel spaces by definition, and this is the category of complete Siegel spaces equivalent to the category of infinity category. So this is just limit preserving functors from B up to cut infinity. And that's what we wanted. Okay, so this is not very hard. I mean, the most tricky thing is probably here okay, I mean, it involves something, it involves this equivalence, and it involves the unit lemma, but given these, it's easy. But somehow this is actually quite convenient in practice because it makes it very easy to produce examples. So let's say you would actually want to apply this, let's say in equivariant homotopy theory or something, then very, very rarely the B categories, whatever B is in the situation that you would like to understand, actually come to you as a simplicial object in some topos, but they usually come as sheaves of infinity categories on a topos, or as pre-sheaves on a topos. So for producing this example, somehow for producing examples, this side here is very, very useful. So this is why this equivalence is nice. So let me continue by giving some examples. So these will not all be like real examples, but some more examples that will be necessary to develop the theory a bit. So first of all, you have some obvious functoriality here. So if you have a geometric morphism of infinity topoi from A to B, then you always get an induced adjunction just by tensoring with cut infinity, if you like, between A categories and B categories. And I will also just denote these by F lower star and F upper star. So this is just if you want to push forward and the pullback of sheaves. You can also think of these, if you like to think of these rather as complete Siegel space object, this is just post-composition with F lower star and F upper star, because both of these preserve finite limits. But I mean, there's already one interesting thing we can do here, namely if you have an infinity topos, there's always a terminal geometric morphism to the terminal infinity topos of anima. So yeah, there's a unique such thing, which I usually denote gamma lower star because someone's taking global sections. And then we get an induced adjunction like this. So we have some way of taking the global sections of a B category. You can think of this of taking the underlying category. of this B category, and it has a right adjoint, which I denote const, which is somehow, which you can think of taking infinity category and taking to the constant sheaf on that infinity category. Okay. So this already gives us some examples
So this,
because,
sorry. If I go one categorically, this is completely analogous to an anima being sets, and then I just look at category in internal to something as a category in sets first.
yes. This is
Okay, cool.
completely analogous. Yes. Yeah, so I mean, maybe this is something that I should have said. I mean, yeah, so I mean, cut infinity, I mean, we can also, I gave this general definition, but I mean, of course, cut S is cut infinity, just like somehow categories internal to sets are just categories. So this is completely analogous to this. I mean, I think basically everything that I'm saying today is probably completely analogous to how it works in one category theory. Yeah. Okay. I mean, there's some differences now that I think of it. Okay. So right, then it's also not hard to see that cat B, so this category of B categories is actually Cartesian closed. So this means that for C and D in cat B, so if we have two B categories, then we can form somehow an internal Hom object between them, which I will denote fun underline BCD, because you're supposed to think of this as the B category of functors between these two B categories. Okay. And actually, if you, okay, yeah, sorry, let me say this later. You can also somehow do something to this object here. I mean, we've already seen that there's a way of taking global sections of a B category. So to look at the underlying infinity category, and you can look at the underlying infinity category of this B category of functors, and then you get the infinity category of functors from C to D, which I will denote in the same way, but without the underlined. Okay. So, and by the way, so the objects in here are, you can, if you think of C and D as sheaves of infinity categories and B, then the objects in here are literally somehow natural transformations between these two sheaves. So somehow this is, you really get here what you expect and not something random. Okay, but in particular, one nice thing, if you have an, if you have these kinds of objects, so if you have Hom infinity categories, that means that you are enriched in infinity categories. So one way of saying is that this tells you that cut B is actually an infinity-2 category. And this is already nice because it gives you somehow, it allows you to already do a lot of category theory. I mean, or at least some category theory you can do internal to any infinity-2 category. So for example, you get a theory of adjunctions. So you can now say just with this observation what an adjunction is, namely it's a functor in one direction, a functor in the other direction, and then some arrows in here satisfying the triangle identities. Okay. Maybe now an example of a slightly different flavor, namely you have a fully faithful embedding from B into B categories by, you can think of this as taking an object in here and sending it to the constant simplicial diagram at this object. I mean, this clearly satisfies these axiom 1 and 2. So this gives you objects in here. And this actually, if you can think of the objects in B precisely as the groupoids in here. Okay, it's just like the groupoids in infinity categories are just anima. The groupoids in B categories are exactly some of the objects coming from B. Okay. Now somehow one more example, and for me at least, this is somehow the crucial example, and this is also why we need an infinity topos. Namely, you can look at this following sheaf here, which I denote B underline, and it takes an object B to the slice B over B. And the functoriality is given by pulling back. So if you want to be precise, this is given, you can define this functor here by unstraightening the, domain fibration. Yeah, I think you take the codomain fibration. Yes, this is a Cartesian fibration, and it unstraightens to a map like this. And this is actually a sheaf. Okay, so this functor here preserves limits. And this is actually the definition of an infinity-topos. So you get this example here as a sheaf if and only if B was an infinity-topos. So if you want this example, you really need an infinity-topos. And I somehow want to make the claim that you really want this example, at least somehow if you want to do a lot of category theory, because, this was the wrong notation. Just switch to this, because this thing here will play a very important role. Namely, it will play the role that the infinity category of anima usually plays in usual infinity category theory. So I will make this a little bit more precise, but for example, Hom functors will land in here, and this is the free co-completion of the point, and so on. So this is somehow a very crucial thing. Okay, so now maybe let me give you some small example of how we can now do infinity category theory in the setting. So for example, you can say now if I and C are two B categories, that C has I index colimits. And I mean, this is now again what you expect. Somehow, if the diagonal functor, so the functor that takes somehow, which is given, it's induced by the functoriality of this internal Hom from the map from I to the terminal object, and you just require that this has a left adjoint. Okay, this is also exactly what you would do in usual category theory or in infinity category theory. Okay, and so this gives you a notion of having colimits indexed by some category. And then you can prove the following theorem, something that I already mentioned, namely this infinite category B underlined, and this is the free co-completion of the point. So in other words, if you want to specify a co-limit preserving functor, so I mean, I haven't defined what co-limit preserving means, but you can probably guess it. It's a functor that is compatible with the left adjoints that you get here. Then specifying a co-limit preserving functor into a co-complete category out of this thing here is the same thing as just specifying an object. Okay, this is somehow why this plays such a crucial role. Okay, so this is something that me and Louis prove, and I think the second of this series of papers. But I guess one question that you might of course ask, which is reasonable to ask, why is such a theory useful for anything?
May I ask before?
Yes,
so
sure.
for the theorem, is this kind of synthetic, or is it? Do you prove it inside quasi-categories, or
yeah? So yes. So I mean, in everything that we're doing, I'm assuming already working theory of infinity categories. So somehow I'm just,
cool.
If you want, I mean, so I'm completely fine with just taking quasi-categories, taking HTT, and somehow just working with that model.
Okay, cool.
And everything
Thank you.
is building on that. Yeah. Sorry, I should have been more clear there. Okay, so I don't know. Are there more questions before I get ahead of everything again? Okay, so now yeah, why is such a theory useful? Somehow in my remaining time, which I now see is not a lot, I want to give some motivation why one would want this. So
sorry, just so you know, we started 5 minutes later, so you have until 35.
Okay. Okay. Yeah. Great. Okay, that makes my situation better. Okay. So right. This is very useful. This theory, if you want to understand geometric morphisms of infinity topoi and especially geometric properties of these. So for example, if you want to understand proper and smooth morphisms of infinity topoi. And it turns out, yeah, actually, I think you can even say that a good theory of internal higher categories or somehow a working theory is actually crucial if you want to have these. So maybe give me some little motivation why somehow I think that this is a claim. By doing something, why this is a true claim, by doing something that maybe sounds a little bit absurd at first, namely I will define infinity topoi internal to this infinity topos. Okay, but this is something that we can now easily do. So a B category X is a B topos. If, and I mean now I somehow just copy the usual definition of an infinity topos. So if there's a small B category C and an adjunction of this form, so X is supposed to be a reflective subcategory of pre-sheaves on some small category C. So pre-sheaves is as usual just functors from C op into this B underline because this is our analog of anima. And you have to put some condition on this. You want I to be fully faithful and accessible, and you want this left adjoint to be left exact. So I mean, there are some words that I didn't define here. I mean, fully faithful, accessible, and left exact. I didn't tell you what this means for a functor between B categories to satisfy these. But actually for all of these, it's very easy. It turns out that it suffices to do all of these section-wise. So for example, if you want to say left exact, it's okay to just say, I take this functor, I evaluate it at some B, thinking of both things as sheaves of infinity categories, then I get a functor of ordinary infinity categories, and I can just ask that to be left exact. So, I mean, it's not a priori clear, but it turns out that for all of these, doing it section-wise is correct. Okay, so we have, this is now a B topos, so an infinity topos.
Sorry, if I take B to be anima, you gave me a different definition of infinity topos, a priori, but it probably turns out to be the same, right?
Yes, it turns out to be equivalent, yes, but that's a theorem in HTT, a very non-trivial one, actually.
Yeah. Okay, cool, thank you.
Yeah. Right. So yeah, we have some definition of B topos, and I can also define again a geometric morphism between them, which is also what you expect. So now a geometric morphism of B topoi is a right adjoint functor such that the left adjoint is left exact. Okay, so these assemble into a category of B topoi. And a little remark which follows from this theorem now quite directly that I had before, this B underlined, this is actually the terminal object of this category of B topoi. Because, well, if I want to specify a right adjoint into B underlined such that the left adjoint is left exact, then this means I have a colimit preserving functor. This means I have to specify a colimit preserving functor out of B underlined into this topos that sends the terminal object to the terminal object, because it has to be left exact, and then there's only one such choice. Okay. So if you believe this, then I can now state the following theorem. So you have a functor from B topoi to infinity topoi by taking global sections. So I mean, this is something that's not completely clear, but it turns out if you take the underlying category of a B topos, you actually get an infinity topos. And we know what the terminal object is. It was this B underlined. And if we apply gamma lower star to B underlined, we get B. So this functor actually canonically factors through infinity topoi over B. And this functor here is then an equivalence. So in other words, this kind of absurd sounding thing, namely infinity topoi internal to infinity topoi, is just the slice category. Okay. But so maybe let me say one thing. I mean, if you know one-topos theory, then none of this is surprising. I mean, in one-topos theory, all of this has been well known for a very long time due to work of a lot of people. And actually, I think it's fair to say that a majority, or not a majority, but a large part of Johnson's book on topos theory is somehow actually, to some extent, about exploiting this passage. Somehow, to at least the part on geometric morphisms is doing this a lot, passing back and forth here. Okay, but now we also have an infinity categorical version of that, and this is somehow on practice, or somehow it's quite convenient, because somehow topos theory internal to B is supposed to be not that different from ordinary infinity topos theory. So every kind of notion has an analog in here, and then this gives you some property of geometric morphisms via this equivalence.
Sorry, I think I missed. So top infinity is with geometric morphisms, and top B is kind of an analog of those with geometric.
Yes.
Okay, cool.
I mean, I think I gave a definition of a geometric morphism of B topoi, which was
thank you. Yeah.
Right adjoint with a left exact left adjoint. I didn't give the definition of a geometric morphism of infinity topoi, but it's the same. It's somehow a right adjoint with a left exact left adjoint.
Cool, thank you.
No worries. Right. So maybe, okay, I only have 1 minute left. I will do this very briefly. So I wanted to give one example somehow where this actually helps you to define something. So for example, you can call infinity topos X compact if the global section functor commutes with filtered colimits. Okay, this is a definition that you can make that is sensible. I guess one motivating example is that if you take sheaves on a compact Hausdorff space, that's compact. Okay, and now you can ask, what's a good relative notion? Well, one thing that you might try is to just say, I want a geometric morphism just to preserve filtered colimits. It actually turns out that is way too weak. And there would be way too many things that would be relatively compact. And therefore, a good definition is to call a geometric morphism relatively compact, but usually relatively compact is what's called proper. If the associated geometric morphism of B topoi that you get, so passing with this equivalence, you now get a geometric morphism of B topoi from this X underlined. So this is just my notation for the image under this equivalence to be underlined. And now you can ask for this to commute with B filtered colimits. I mean, I don't have time anymore to tell you what this means, but it's again not hard. You can just ask for the colimit functor to be left exact. And then you get somehow a different notion of relative compactness, and this turns out to be the correct notion, because you can then show that it's being proper in this sense is equivalent to satisfying proper base change, somehow also being proper in the sense of Lurie. Okay, but yeah, maybe I should stop here because I'm out of time.
Okay, let's thank our speaker. Thank you very much for the talk. And are there any questions? So feel free to unmute yourself or write in the chat. I see Ivan has a raised hand. Please, Ivan. You are muted.
So I have a question. So actually two questions. The first one is, do you have a theory of internal sites also, or are you working on it? And then the second question is, you mentioned that there is actually some difference with one-dimensional topos theory. I would like to know which one. And I would have actually other questions, but we can start with those.
Yes. So I mean, there certainly supposed to be a theory of internal sites, but we have not properly developed that. But I actually would think would be a good motivation for doing this because, yeah, I don't know. Because I think even if you want to specify some more, if you want to give a good definition of morphism of sites, just of usual sites, I think something like this, having some internal sites, could already be useful to correctly state something like flatness. So yeah, but we have not worked this out, and we are also not currently working on it. Somehow moved in a slightly different direction. So yeah, that was the first question. So maybe then the second question. I think one thing, I mean, which is the thing that I had in mind, that I said that there is something that's different. I mean, there's several, but I mean, one thing the way you always have to be careful, where actually infinity category theory is nicer, is this statement here. I mean, the one toposic analog of this is not true. Somehow it's only certain limits that are preserved here. I mean, you still somehow get this object here, and you can still somehow make sense of presheaves and so on, but it behaves slightly differently, I think. But sorry.
But this is a fake difference in the sense that in that case you would take just the subobject classifier, and here you need this guy, which is a walking universe for you.
Yes.
There,
yes.
the subobject classifier would be enough, and like
yes.
Of course, it is a difference, but you just change the name of the guy, and
yeah,
the same, right?
Yeah. Right. I mean, so in this sense, this is not a real difference. I think you're right about this. So, I mean, one other thing which I think which I personally find interesting because it's different, is somehow this notion of properness. I mean, you have an analog of this result here. So careful. This is what Murdak and Vermeulen and general people in one-topos theory would call tidy and not proper. Somehow there's a mismatch in terminology here. But somehow, yeah, we decided to follow your Lurie's terminology and just call this and stick with proper and not tidy. And somehow here the difference is that some of the prime examples of, yeah, maybe let's stay with compactness. Some of the prime examples of compact infinity topoi are coherent topoi. Of compact topoi, one topoi, are coherent topoi. And this is somehow very crucial. I think somehow, even if you look at the proof of Murdak and Vermeulen, even the proof somehow revolves around that idea in some sense. I mean, you need these kind of compact sites. And I mean, an infinity topos theory is just not true. So it's not true that a coherent infinity topos is compact, because the global sections functor typically does not preserve filtered colimits only for n-truncated objects for every n. So it would be something that you could call almost proper, but they're not actually proper. And I mean, the difference is, of course, that in the infinity world, and this is somehow a cause for a lot of trouble and all of these differences between hypercomplete and Postnikov complete and so on, that the sheaf condition is a simplicial limit. This is an infinite limit. This does not obviously, or typically does not commute with filtered colimits. And this is somehow where the problems come from. Yeah.
Is the terminology proper coming from some algebraic geometry, or is it just random kind of?
So I think maybe one should not say, it's probably more coming from topology. So I mean, there's an example that I didn't say, but yeah, here's the example. If you have a proper and separated map of topological spaces, so proper is just the definition of, they have the usual definition, a preimage of something compact is compact.
Okay, cool.
And then the push forward is proper.
Okay, cool. Thank you.
Nice.
There's one more question by Antonio.
Yeah, I wanted to know exactly how to relate this thing with categories, normal categories. Like, if you start with an infinity category, you have an underlying category. And now I was wondering, like, this internal notion of categories, does it commute with this underlying functor?
So by underlying category, you mean the homotopy category of an infinity category?
Yeah.
Yes, I mean, I think usually this is supposed to cause trouble. And I think it does very much, actually, because I mean, this is one of the main advertisements where people say that infinity categories are cool, because examples like, if you look at schemes, for example, if you take a scheme X and send it to QCo X, so to the category of quasi-coherent sheaves of X, if with QCo you mean the infinity category, the stable infinity category of quasi-coherent sheaves, that's a sheaf on the category of schemes. But somehow if you take homotopy category, it's no longer a sheaf. So taking homotopy category destroys this property of being a sheaf. And therefore somehow it's also not clear at all that if you have somehow an internal category internal to some infinity topos, that if you take the homotopy category, then somehow, yeah, you would have to sheafify again or something, and this would be unreasonable. So I think it's probably I don't know, to me it feels more reasonable because of these examples to stay in the infinity world. But I mean, there certainly is something to be said about the passage. I mean, it's probably still true that you can define something like a one category internal to an infinity topos by saying something like the mapping space is a one truncated, zero truncated. And then you probably have an inclusion from one categories to all infinity categories, and this is supposed to have a left adjoint. So there is something here that you can say. There's some analog of the homotopy category, but I think it's going to be a bit subtle because of these issues.
Okay, thank you.
There's one more question by Ivan.
So the first two questions, one question and a comment. The first question is, so you mentioned that now you moved away from the general topic of sites, which yes. So I wanted to ask you whether now you're working on something related or you really changed the topic. And then I have, before you answer, a comment concerning the definition of proper versus tidy. Mm-hmm. The comment will sound a bit technical, but actually there is some concept behind it. I would call your notion of proper infinity proper against zero proper, which is really like localic truncated. And okay, I see you say yes, so you understand what I'm saying.
Yes,
I think this kind of n truncatedness is relevant in the theory of proper morphism of topoi.
Yes, I mean,
saying yes, so fair, fine, okay.
Yes. So actually, me and Louis in this paper, we actually also give some notion of n proper for every n. And somehow also the result here somehow still works for every n. Yeah, you're very right.
Good. And so what are you, now you changed topic, you don't work anymore on this?
I mean, we're still doing some internal stuff. So, but somehow the thing that I've been thinking about most recently is doing K-theory in this setting. I mean, there have been some recent breakthroughs on with doing K-theory of dualizable categories. And I mean, there's this typical example that if you take sheaves on a locally compact Hausdorff space, it's a dualizable category. So you can take this continuous K-theory, is what Efimov calls it, of it, and you get some compactly supported cohomology. And I want to relativize this. Somehow there's supposed to be relative versions of this. And this is also supposed to have some applications, I think, in geometric topology, because somehow it would allow you to define relative assembly maps. And I think, so we're still doing something like that. We're still doing something like this, but it's more K-theoretic at the moment. Yeah.
Okay, thank you.
All right, let's thank our speaker again for a great talk.
Thank you.
And